provided I can actually do something right this period. Last period, I seem like I messed up a couple things. Make co-host. Oh, I already did. Good for me. Good for me. Questions, comments, concerns, anybody? Well, I'll just throw this out there. Next week I'm going on vacation. So we're not having class next Wednesday. There's already content up for that, so it's not like you're gonna miss anything. And I probably won't have office hours. I'm not gonna guarantee it because I'm gonna be kind of Eastern Oregon up in the sticks. So I may or may not be able to have office hours. Stay tuned for that. I will be able to check in via email every day, probably most days anyways. I'll have my computer with me. So if you have any questions, let me know, and I can work them out and send you at least the work, maybe a video too. I'm not sure how fast I can upload from over there, from where I'm going to be at. And then, what was the other thing I was going to ask about that? Oh, when you send me an email, somebody in the other class emailed me the other day, and I don't know. Apparently, I thought they were in the wrong class. Maybe, I don't know. And so, if you have any questions, specify what class you're in, which most of you doing a pretty good job of that. And then also, maybe take a picture of the book, especially next week. Take a picture of the problem you're doing, because I probably won't have my book with me when I'm on vacation. So, yeah, I guess that's that. And then I can answer it and get you back on the right track. So, hopefully.
I have one question, sir. I joined a little bit late. What dates were you talking about being gone?
Oh, next week.
Okay, thank you.
So no class next Wednesday, and all the content's up already, so it's not a big deal. And then I'll try to do an office hour on Friday, but I'm not going to guarantee anything. Next Friday, but I'll try, but I'm not going to guarantee anything because I'm not sure exactly where I'm going to be at and what kind of internet I can have. So, okay. No questions on homework at all? Anything? Nothing. Well, that's too easy.
Nothing.
You guys are. Is it fun or is it just kind of?
It's all right.
Yeah, that's exactly right.
Yeah.
Exactly. So I think today what I wanted to talk about, again, kind of these class sessions, I want to be more about the why do we do things. So I was making a video the other night for this class actually, and it hit me. And I think that once you're listening to that video, or when you're watching that video at some point, and you will one of these days, you'll kind of see how it all kind of blends together. But the idea of set theory kind of overarches a whole bunch of things. So it overarches probability, obviously. Okay. It overarches some logical stuff. Now, who's chatting up with me here? Yes, I am recording. Thank you. And it overarches some things with the equivalence relations, amongst other things. So the idea why we do set theory, kind of because it kind of blends across the whole thing. So some things, you've seen it this week a little bit. Oops, what am I saying here? If you say, A union B, obviously marrying them together, this really could be thought of as or. Later on, when you get to logic, this is going to change to this style. Okay, it means exactly the same thing, and you're going to see that when you get there. But all of these same concepts, this is, of course, the intersection, which of course means and of course, when you get to logic, it's going to be written like this for no apparent reason that I've ever been able to figure out. So just be aware of that. Sorry, what chapter are we going over? Little 6, a little bit of 8, a little bit of this, a little bit of that. This kind of goes over everything of it. So it's a little more of the how comes, okay? And the why are we studying set theory, okay? If all you ever did was say, all right, A is this set. This is exciting. 1, 2, 3, 4, 5. And like B is this set. Oh, that's exciting. All right. 2, 4, 6, 8. Hey, what is A intersect B? I don't know, man. And then you do it and you're like, oh, let's see, they have 2 in common and 4 in common. All right, there it is. Isn't that fun? No, it's not fun. It's boring. It's stupid and awful. It's terrible. It's terrible. The reason we do that is because if you were doing something like this, and let's say these are all part of a greater set, there were the numbers 1 through the integers 1 through 10, while that could be thought of in probability as your sample space, these are the integers 1 to 10. Here are these specific ones, 1, Actually, let's do this first. So in the middle between them, when they intersect, is the numbers 2 and 4, obviously. And this one has 6 and 8 in here, and this one has 1, 3, and 5 here. And then, of course, what's missing? 1, 2, 3, 4, 5, 6, 7, and 9, and 10, right? Those guys would be out there. So why would we say this? Well, it'd be the probability of getting something in A and B would be there's 2 of them out of 10 of them, right? So that'd be your answer. So obviously it matters when you're discussing ideas of probability, clearly. It's stuff we've been doing. In fact, it'd be the probability, oh, what just happened? Oh, fart, it did that again. No, here it is. It'd be the probability of A and B is written, of course, and your book actually writes it like this. It's A intersect B over S in this case, right? It's the total numbers of them. Okay, it's the whole sample space. And so there's a reason why we talk about these. That the reason that I do set theory after probability is because I think that it gives you something to hang your hat on. Okay, it gives you a reason for looking at it. When I learned set theory back in the day, it was its own class, and literally there's an entire quarter of nothing but set theory. It was awful. Because it was just this, let's look at this, let's do these, let's do this. You're like, okay, what's the cardinality of the set? Oh, for God's sakes, nobody cares. Nobody cares. But when you say to me something like, hey, where'd you get the 10 from? Well, it's how many numbers are in the set. Oh, cool. What do you call it? Well, it's called the cardinality of the set. Then it starts to make sense because it starts to then ground what you've learned in something that you already can wrap your head around. That's, in my mind, learning always takes place from a standpoint, it looks best anyways, when it starts with something you know something about, and then it goes out from there and you learn something new and how it relates to what you already know. In my mind, that's the best way to learn. So that's why I do probability first. That, and it feels to me like you can people have by the time they got into this class anyway, you know something about probability, so it's not terrible, and you can kind of jump in and go from there. Okay. So we'll be looking at that quite a bit. So I was just shooting a video the other day for chapter 2, and in chapter 2 we do logic stuff, and I will show you kind of an example of this, and I just want you to kind of see how these pieces work together so that you can see that, hey, there's a reason why we're doing this. And if I can find the picture that I wanted, I will show it to you. Yes, no, that's not it. Where did it go? My book closed. Alrighty then. Oh, for God's sakes. All right, we'll come back to that in a minute after I find this, I guess. Where? Swear it was on page 54, but it's not on 54. All right then, well, tiddly diddly. Oh, there we go. Yep, there it is. It's on 35. No, there we go. Cool. So, you will see a problem that looks something like this later on, and you'll be like, oh, what does that even mean to me? So, for instance, not P and Q like this, and P, not P and not Q, okay? So the questions are, we want to know whether these are logically equivalent. So the stuff that we're studying right now has to do with sets, number one, okay? So we're talking about set theory right now. And this week we're going to be talking about, later in the video this week, we're going to be talking equivalence relationships, okay? So when we get to chapter 1, or back to chapter 2, when we get into some logic, it's taking the same things you're learning this week, and you're looking at it from a slightly different viewpoint, okay? So what I'm going to do here is I'm going to draw this box I had a minute ago, or something very similar to it, I guess. Here are the numbers. Actually, I'm just going to copy it from the previous page. I'm just going to copy this doodad here. And I'm going to copy it and paste it over here. And instead of A and B, I'm going to change them to P's and Q's. There you go. Cool. P, Q. Okay. So again, the reason that we're studying this stuff is because we're going to use the same techniques, the same everything when we get into chapter 2. It's going to keep coming back to us. Now, this little doodad right here means not, or the negation. Wait, what does that sound like? It sounds an awful lot like P complement or P complement, whichever way your book writes. I think it's this way. It's not P, okay? So let's look at this. So what they want us to do is this. It's P intersect Q. Well, where is P intersect Q? Well, P intersect Q is this guy right here. Those guys in there, it's the 2 and the 4. Well, let's look at that. Okay, so that's who's in that set right there. Who is the opposite of that set, or who's not in that set, in other words? Well, it would be these guys, and these guys. That's supposed to be a highlighter. I guess it is a highlighter. Okay, can everyone see that? So not P and Q are the green ones that I've highlighted. I'll put a little green here so you can see that. That makes sense? So then the question is that the same, oh shoot, is that the same as saying not P intersect not Q? All right, well, let's look at not P. Not P would be this and this, yes? And so that's not P. And then where is not Q? Where's your, get your right? Not Q would be these guys and these guys, okay? Well, where does the pink and the yellow intersect? Well, the pink and the yellow intersect where, somebody? Where do the pink and the yellow intersect?
7, 9, 10.
The 7, 9, and 10, right? So this over here, these guys would be, right, would be 1, 3, 5, 6, 8, 7, 9, and 10 in no particular order. This guy here would be 7, 9, and 10, okay? Are these the same? Are they equivalent? No, they're not. It's not an equivalent relationship, which is what we're going to call them this week in chapter 2. It's exactly the same stuff. In chapter 2, what we're going to say is, no, they are not logically equivalent, okay? So what I want you to see is that once you get done with this week, not everything, but most of the stuff we're going to see the rest of the book, what we've already seen in probability, and then from what we see the rest of the book, it's going to be exactly the same stuff, kind of regurgitated and kind of used a little bit differently, okay? It's kind of like if you can fix a car, you can probably fix a lawnmower pretty well. It's just the things transfer over, sometimes easier one way than the other way. You know, if you can fix a lawnmower, you may or may not be able to fix your car. But if you can fix your car, you can probably fix the dumb lawnmower. Okay. Once you understand those concepts, they're for the most part the same. They're just being used a slight bit differently. Okay. So then, what would this mean to me? Well, this just says this: that if you take the opposite, or so how do I want to write that? Not A and B. That is not the same. It's not the same as not A, or not A and not B. They're not the same. And so that's a big deal because people oftentimes, and logically speaking, will try to use them interchangeably, and you'll run into problems if you do that. Now, in the video yesterday that I made for section 2, I spent a great deal of time drawing Venn diagrams. I like Venn diagrams. They make me happy. I can see what I'm doing. It's pretty straightforward. I usually draw them as if they're intersecting circles. I usually do that to make it makes the most sense. But it's quite possible if there is no intersection. That's cool. That's okay too. And we can see those things. What if, for instance, we had a situation like this? And again, this is a blend of chapters 6, 8, and 2 with a little bit of chapter 10 probability sprinkled on top, okay? So if you look at this, if this was, I don't know, high school, let's see, so pre-calculus, sure, people in pre-calculus. People in pre-algebra, well, I'm gonna write that over here, pre-calculus, pre-algebra, which by the way is just pre-calculus, right? And then language arts 10, look at me go. So where would I draw those other circles? Well, I feel like language arts 10 would clearly intersect. You'd probably have some sophomores in both classes, okay? Would you have people in pre-algebra in pre-calculus? No. Would it be possible that you have pre-algebra people in language arts 10? Yes, it's possible. It's not great, but it is possible. Is there a kid perhaps that's out here somewhere? Yes, he is a freshman that's in calculus or something. I don't know. Maybe he's a freshman in algebra 2. I don't know. But he's probably not in sophomore English, and he's not in those other classes. It's totally doable. If we call this one R and we call this one, oh, I don't want to use S. That's too hard. Let's do A, B, and C. How about that instead? A, B, and C. Okay. If a person said to you, all right, well, let's look at this here. So what is the can you sketch or draw out what P or A complement intersect B would be? Well, where would A complement intersect B lie on this thing? So I'm going to get out my marker here, and we're going to see if we can draw that out. All right, so where are you going to be? A complement intersect B. Where would I find that? Where would you find that? Anyone? We'll wait. How would I draw A complement? Where's not A at? Anyone? Look at you people. You do what I do to my principal. I just turn the meeting on and walk away. What's that?
Not A is B and C.
It is B and C. It's everywhere, not in A.
Right.
So it's literally everywhere, including those guys. It's everywhere, not in A. Okay? Everywhere, not in A. Be very specific. It does not include that little corner of A. Okay, right there. It doesn't include that at all. That is A complement. Okay? Now, where is B? Well, B is this guy. It's everything in this circle. Okay? Where do they overlap? Well, they overlap right here. Well, that is terrible. You can't see that for sour apples. There it is. That is where they overlap. It's all of B except the part of B which is inside of A. Okay? So that's what we're talking about. Now, what would that look like from a probability standpoint? If you were to use what I just wrote up here, if I try to use that in a probability question, it would be something along the lines of, hey, what's the probability of a person who is not in pre-cal and is in language arts 10, okay? Or another way to say it, the probability that you're in language arts 10 and not pre-cal. Another way to write that would be to say the probability that you're in language arts 10, but not in pre-cal. And in fact, in logic, the but takes the place of and, okay? And you can see right here where it comes into play, because normally that's what you'd say. Look, I want a language arts 10 person, but I don't want someone who's in, but they cannot be in pre-cal. And so when you say it, but not in pre-cal, what you're really saying is, and they're not in pre-cal. It just sounds better to put a but in there, okay? So in logic, we actually do that. They take but and they swap it out for where you normally put an and in probability class. That's where you put it in, okay? And that's the idea. And so then, of course, it would be whoever is in this yellow area divided by the total number of people in the entire box, right? In everywhere in the entire box. And so what I want you to see is that things are always going to be the same no matter what we do, okay? Whether it's in chapter 6 with logic, whether it's in probability, or whether it's in logic later on, all the same thing, okay? And the sooner you get a grasp on that, the easier it makes your life going forward, I think, when it comes to probability-wise. The rest of your life, you're out of luck. But probability-wise, set theory-wise, the sooner you can wrap your head around that and say, oh, look, if I look in terms of a Venn diagram, piece of cake. Okay, let's do another one here. Let's do B. Sorry, let's do A. Let's do A and B. Let's do it with an intersection though. A and B. All right. Complement. Nice. Union. Union C. Yeah, I like that. Okay, here we go. So where would we draw this? Let me grab this picture up here. It's freaking me out on my computer screen. I thought I saw that my screen was broken, but it's just part of this weird, the calculator thing's like hiding behind it. It's freaking me out. All right, give it to me. There you go. Nope. Let's cut this baby out. Nice. Copy. Here we are. Paste. Oh, nice. Okay, here we go. So where would A and B complement lie? If you were in A and B complement, where would you be? Okay, can you all see that? Oops, where's B? You erased it, stupid. Go ahead. Oh, wait. Okay, who said it? Someone's got a word for me there? Ones. What does ones mean? Laura, was that from before?
Is it where A and B meet up?
Oh, I see. Gotcha. So, okay, so A and B. So A and B is this thing, yes? So what would the complement of that be? What's the complement of that? The complement is everything else, yes?
Right, both sides
So,
of A and B.
so it'd be all of
Everything
this,
else.
all of this, all of this in there. The only thing to be left is that A and B part right there, okay? So I want to take that and I want to take the union of that with C, okay? So when I take a union, I'm just going to take them and I'm going to slam them together and create some new place. So my new place is going to be included with this guy and this guy right there. Now you're like, wait, I'm sorry, wait, hold on. So I want A and B complement. So that's the pink stuff. So I want the union of this guy here, which was oops, I wrote it backwards. Let me get my right colored pencil out. So my pink pen is this stuff right here. That's the A and B complement. Now my orange pen is this, oh, fart. Well, that's disturbing. Well, whatever, that color down there is C, okay? So when I put it together, what do you notice about this guy relative to this pink stuff? It's already all in that pink stuff. You with me? Does that make sense? Because it is in fully owned subsidiary of it. In other words, it's like saying it's kind of hard to, well, I was going to say be a grandpa if you're not a dad. I guess that's a pretty good one, right? So like grandpas are a special subset of dads. That's just kind of how that goes, right? You kind of hard to jump past being a dad, whether it's stepfather or whatever. But if you've been a dad at some point, you could be a grandpa. That's true, but not all dads become grandpas, I guess. So it's that idea of that. So if you look at this from a logically speaking standpoint, that just means this thing right here, that's disturbing, is really just equal to this guy. They are equivalent. And so that is why we study the idea of equivalence. That's why we talk about these situations, because in here, this whole thing here can just really be written as just this, because this is a full subset of that guy right there. It's completely contained by that subset, okay? That subset is completely contained by the other bigger subset. If there were names in there, like if there were names in this group, there'd be like, I don't know, let's say there's Bob, Joe, whatever, and then Sue and I don't know, George, and then whatever, and Daisy and Sue, and I don't know, Susie, I guess, whatever, I don't really care. All of these people are included in, these guys down here are included in the pink already, and they're in the orange. So because they're already in the pink, I've already got them. Now I'm going to add the orange as well. It doesn't matter, doesn't change anything. This is our final answer, okay? That's going to be a big deal because in section 2.1, we go 2.1? Yes, 2.1, they go through a whole bunch of logical conclusions. And in those, every single one of those is based on the idea of set theory that we're talking about, like right here in a picture, like this guy right here, okay? That idea that, hey, this is a fully owned subsidiary of it. This one's completely enclosed by that. I didn't have to add anything more to it. It's just all right there, okay? I'm gonna try copying that picture again. Kind of happy with that picture. That's cool. Suppose you did something like this. Let's do let's do A complement, sorry. A complement, I forgot what I was doing right now. And I said A complement or C, that's right, intersect B. Cool. All right, so let's look at that. So when in doubt, you're like, I don't know what to do first. Well, first thing you do is take the complement of that, okay? And then after that, we're going to do unions and intersections, and typically we're going to have to include a parentheses to show which way to do this thing, okay? So if I do that, let's look at it for a second, okay? A complement, if you were to draw that out, what would it look like? Where would I shade? I would shade everywhere but A, okay? Now I like it on this pad. I like shading on the pad. In real life, I have a hard time with what do you call it, highlighters. I use a pencil. I shade all one direction and then I shade the other direction. I see where the cross hatchings overlap. I find it really obnoxious to write over top of highlighters with highlighters. But for the purposes of demonstrating, I understand how it works better that way. This thing here, union C, is what? What's the answer to that? If you take the green and C and put it together with C, what do you notice?
It's already
It's just A complement, isn't it? Does that make sense? A complement covers that entire thing. So I'm just going to write this right here is equal to A complement. Now what I want to know is, where does A complement intersect B? Where does this green stuff intersect B?
where it's not overlapped with A.
Exactly. So it's this guy here. And I feel like I've done one similar to that before, but there it is. It's all that yellow stuff is equal to the yellow in this picture. Okay? And that's just it. Okay? So that is kind of what we're doing with set theory. I want to do a couple more here, and then we'll kind of just play it by ear and see what you find out. See where we end up, and then we'll kind of go from there, I guess. Okay. Suppose you saw this guy. Yes. Suppose you saw P intersect Q union R. Okay. What do I know, Jay? I don't know. Let's find out here. Okay. Jay, I don't know if they intersect. I don't know either. So we'll just pretend that they do for a minute, okay? And these kind of problems, we're just going to pretend as if they all do. Okay. So check this out. This piece right here says to do what? It says to take Q and R together. All right, we can do that. So, oops, stop it. So there we go. So I just want to put Q and R all together. So I'm just going to highlight them with the yellow. Okay. And then the question is, where does that intersect with P? Okay. Well, I think it's pretty clear that it intersects with P right here. So this whole bit right here over to here is my answer, right? Is equal to this brown. Okay. But in chapter 2, you're going to take us a step further and you're going to check it out. What if I did this? Oops. What does that kind of look like to you? If this was a plus sign and this was a times, what does that look like? What does that look like? I'm talking to myself here, people. This looks like the distributive property, yes? You with me on that? So if you distribute, you get PQ, so P and Q. Where is P and Q at? So the reason that we study again this stuff is when we get to chapter 2 and you're going to get into, oh, fart. And in chapter 2, you get into logic. In logic, it's going to be all about where these things are, and then are they logically equivalent to one another? Okay. So if I look at this, where's P and Q? Well, P and Q is this thing. And where is P and R? P and R is, I don't know, this stuff. Okay. And so where is the union of the red and the black? The union of the red and the black is this thing right here. Hey, that's the same as what I had before. I should actually write brown. And so what does that tell me? it tells me that they're the same. And so in logic class, because we know our set theory, we say these are logically equivalent. Okay, so what I want you to see is just kind of how this all fits over the entire thing. And we're going to spend a bunch of time on this in chapter 2, but it's all based on set theory. So once you understand the concept of intersections and unions, and in probability we'll use either complement, A complement, or A complement like this, and set theory we'll use those. In logic we use not A. It's the exact same thing, just kind of comes at it from a different standpoint. Why? I don't know, dude. No one asked me. I'm not smart enough. No one cares what I think. So no one asked me why that is. I just know that, well, that's how it is. But again, everything that we do will be because of that. Okay. And so that's kind of the thing that I kind of just wanted to make sure that everyone feels comfortable with. You feel okay with set theory at this point? Everyone feel okay with it? Yes, no, maybe so. No.
For now.
I think just need some more practice.
Yeah. So I personally, if it's me, I really prefer, I like to look at, I like to look at, you say, maybe. I like to look at a Venn diagram because I think that a Venn diagram is the easiest thing on the planet to draw. And when you go to shading, it helps everybody understand what's going on, okay? Another thing that will come up from time to time, I'm just going to go ahead and do that one as well, is if you had another Venn diagram. I'm not sharing. One moment, please. There we go. If you did A, okay, let's do this. Yeah, let's do A. Let's put some numbers, some things that make sense. So this is math 327. This is some engineering class, electrical. We'll call it electronics class. Electronics, sure. Electronics. This is some programming class. Right, so it's probably not terribly likely that an EE guy is sitting right here, okay? But a software person might be sitting in here. Well, a software person will be in the programming class somewhere probably. That software person would be right there. Then that person is probably doing some kind of controls of electronics or something. So maybe there's a crossover. There's a crossover between all of them. But if I said to you this, listen, I want the probability that I find someone who is just in 327. When I say that, what I'm really trying to say in parentheses is like this. I'm really trying to say only not programming or electronics. That's what I'm at. That's what I'm really asking here, okay? And so there's others out here, other folks out here, which I'm not interested in them either. So when I do this, okay, if I'm doing this with this situation here, what I really want is, so the whole box has a total number of people. Total number of people is some S, let's say. So I know S is going to be my denominator, okay? Well, the question then is what? Well, you're going to need to take A, right? And you're going to need to subtract off of that what? Well, you need to subtract this piece here off, yes? This whole piece right here. Now, be careful when you do that, because what have you really done? Well, you got to be careful, because if you, if you subtract this whole wedge off, you've also subtracted part of B, yes? So what I need to do is this. I need to subtract the A intersect B. Oops, well, let's do C, that's the one I wrote, right? And you need to subtract A intersect B, right, which would be this piece here. But what did you do when you did that? Well, you subtracted, what is this piece right here? This is, you need to add it back on, A intersect B intersect C. And why do I say that? Because when you subtract this, you subtracted it one time, you subtracted it 2 times, but you really only should have subtracted it just the one time, okay? So you can add it back on. So when I was a kid, I remember the first time I ever saw someone do this to me, I'm like, freaked me out. I'm like, what are you doing? And it didn't make any sense. But as soon as someone came along and said, listen, there's 20 people in this class total, or it was 20 people there. I'll just put numbers where I want them. How about that? There's 20 people here. There's 11 people here, 2 people here, 6 people there, 30 people here, 3 people here, and 22 people here, and 100 people out here. If you were going to go find this answer, you would just say, listen, it's 20 out of the rest of them, which would be 36, 38, 41, 52, 74, 170, 194, I think. Okay. And that would be your answer. Okay. And it's pretty straightforward. But if you think about it, the probability that a person is in A is 26, 28, 39. Yes. Okay. The A and C together is minus 13. A and B together is minus 8 more, right? And then we need to add those 2 back on. So if you do that, that's going to be 39. That's minus 19, which is, how about that? 20, okay? What I want you to do is always be able to go back and look and go, does this make sense based on a probability situation? And for me, probability is where I don't want to call it my happy place, but I enjoy living in probability land. Probability makes me happy from the standpoint of, I look at that and I go, probability kind of makes sense to me whenever I do things. Okay. Sometimes set theory, I get a little, I don't know, confused is not the word I want, but it's not the most clear, obvious thing for me. But when I look at it in terms of probability, I'm like, yeah, that makes sense. I can see that happening. Okay. And again, why would I ever want to do A minus A intersect C? Why would I ever want to do that? Well, because I want to get rid of the ones that are in there. We already talked about this earlier. We said something like, where did I write it? Up here somewhere? Nope. Down here? Oh, I said but somewhere. Do you remember when I said that? I don't remember when I said that. Oh, yeah, right here. Yeah, right there. Boom. In LA10, but not in pre-cal. That's exactly right. What I'm saying is they're in LA10, but not in pre-cal. So what I'm doing is subtracting this bit off. So I am doing LA10 minus LA10 intersect pre-cal. Okay, and you will do that quite a bit. We actually have already done that again in a probability situation, whether that's in a Venn diagram look or whether it's in a pivot table look. If you go into a pivot table with your probabilities, whether it's an actual table of data like this, or you created your own pivot table, male, female, I don't know, ketchup, hot ketchup, mustard, relish. Favorite condiment, sure, I don't know, whatever. I don't know, whatever, good enough for government work, okay? So what is the probability that you get a female but not a relish person? Or another way of saying that would be to say female, okay? A female who is not a relish person, right? A female who is not a relish person, who is not a relish person. Okay, now I could draw this up a couple of different ways, but really what I'm interested in is the female bubble, okay, and the relish bubble. In the female bubble, there's 22 here, there's 26 here, and in the relish bubble, there's 6 more over here, and then the rest of the people are, the other 40 of them are out here. Is that right? Okay. And so when I look at that, I'm like, all right, well, let's get a denominator, 46, 72, 94 total people, I think. And of them, who am I interested in? Well, I'm interested in the 48 women minus the 26 relish people. And you're like, Jay, wouldn't you just do 22 out of 94? I would. But the idea of why you just ignored those is because you realized that of the 48 women, you didn't need these people, and you just looked at the 22. You're doing the same thing. You're doing it in your head, but you're doing exactly the same thing. And that's kind of what I want people to be confident about. Okay. Oh, was it Annie? Was that you was asking about that? Yeah, it was, huh? That's right. Yeah,
It was.
yeah.
The question where you can't have ketchup and mustard on your hot dog.
Apparently, I wrote the question, then yeah, she didn't. She made me actually think about it. I'm sorry. I didn't think about it. So yeah, it's just your favorite condiment. Like sauerkraut, everyone knows is the best. Okay, condiment on your hot dog. Doesn't mean I don't take I don't take ketchup too, because of course I do. But yeah, so I guess it was just your favorite condiment. But the
Right.
idea of that is just that's kind of how they're working out then.
It's easy to overthink these problems, I feel like.
Yeah, yeah. Well,
Yeah.
and it's hard to write them too, because sometimes I try to write them to where it's fairly clear what I want. Other times I try to write it so that it's a little open-ended, so that I want to see what you know or don't know. So I like to write them that's a little open-ended.
I
So when you
see.
read them, you're like, well, it depends. Oh, good. What does it depend on? And then you tell me what it depends on, and then I'm like, oh. Sometimes you talk a lot, and I realize that you really don't know what you're talking about. And sometimes you talk a lot, and then you really know what you're talking about. And then I was like, yes, I nailed it. This person really knows it. So that I try not to do it on every problem, but I do like to have some that are kind of open-ended and it like they're open
Yeah.
interpretation.
I noticed that with the quizzes. I don't want to say too much on how I answered it now, but there were some that I felt like, okay, this is left kind of open-ended, and I'm gonna write down what I'm assuming
Mhm.
so that you know where I'm at with the answer.
Mhm. Yeah. So I don't think anyone's on the quiz were terribly open-ended on purpose. I don't think. But that's cool. If you tell me what you're thinking of, that
Okay.
yeah, too. But yeah, definitely on the test, I'll leave a few that are somewhat open-ended, and I want to be such that really it depends on how you look at it. Some of them are. Some people think that everything's open for interpretation, and that's not true. So, like for instance, running a race or something, order matters in a race. It's not you don't do it for fun. Oh look, doesn't matter where I finished. Okay, we're not two anymore. Um, if you're running a race, you did it for a reason. You want to you try to win the race, and if it come in second or third place, if that's it's a race that matters. So no, that's not open for interpretation. But if it was a situation where I don't know, you read it and you're like, it could be read this way and it could be read that way, and you explain it to me, I'm perfectly happy either way. Mhm. So again, that's kind of where I just want to, when you get to these things, just kind of keep this in mind. There's a bigger reason we're doing this. And I cannot stress enough that I normally am not a big fan of Venn diagrams, but when it comes to set theory and when it comes to logic, I can't do it without it. I have a really hard time doing them without drawing a picture. Okay. And so I typically always do, especially when I'm trying to, like yesterday, I'm making the video for you for yesterday for part of some of the chapter 2 stuff. I was looking at that and I'm like, I can't, one of them I was able to do, one or two I was able to do without writing it down, but the rest of them I can't do it. So I just write it down. It doesn't take very long, but as soon as I write it down, I'm like, oh, well, it's pretty fixed obvious what the answer is. But that picture is just, it's so necessary for me anyways. So if you can do without it, good for you, but that is not Jay. One more thing I wanted to just mention a little bit about, and that's modular arithmetic, and it's in the videos this week. Just want to kind of go over it a little bit with you. We'll be using this quite a bit as well for a couple of reasons. One is that they use it a ton for in the process of doing equivalence relations, because that's kind of a big deal. It's one thing where, and we'll talk a little bit about it here for a second, the concept. But then also we're going to use it when we get to coding later on, and I don't mean coding like Python or something like that, but like UPC codes, ISBN codes, VIN numbers, and any other code that comes along. They all have some kind of a modular structure behind them. This morning I took a picture of a VIN on one of the cars at the school. I was gonna check something out about it, and of course my camera didn't get it. I took a picture of it, but it was sunny out at that time, but the only time it's been sunny in the last 3 days. But whatever, and it blurred it just enough that the last letter I couldn't read properly, and then I must have made a mistake on one of the other ones too, because I typed it in, the computer can't find it. All right, well, the reason it can't, or it says it's not a valid VIN, it knows that based on the structure of how a VIN number works, which we'll talk more about later on. But one part of that is what's called the modular arithmetic. So if you've seen this before, cool. If you haven't, that's nice too. If it was 10 o'clock in the morning, 10 a.m., what time in 4 more hours? Well, of course, it'll be 2 o'clock. And of course, that what you're saying is that 10 plus 4 is equal to 2, which seems ludicrous, but it's really not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 0. That's our clock. And so clearly, if you go from here, 1, 2, 3, 4, it puts us here, piece of cake. But how do you take this guy here and get this? Well, the idea is you take 10 plus 4 is 14. 14 divided by 12, because there's 12 hours on our clock. 12 goes into there one time with a remainder of 2. This guy right here, this remainder, is what our answer is going to be. And so what we say is that 14 is equivalent to 2 mod 12. Okay. And then there's going to be a whole bunch more numbers like this. So not only 14, but 26 will be the same. So what did I do? Because I went from here, I went around 12 more, right? 38, 46, 50, stupid, 50, 12 more is 50, 62, dot, 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 yes. And then going the other way, 2, and then if I'm going this way, I'm subtracting 12. So if I subtract 12 more, where am I at? I'm at negative 10. Wait a minute. What would negative look like on this clock? Well, positive means I'm going this way. Negative means I'm going this way. So if you start at 0 and count back negative 10, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see negative 10 is equivalent to 2 on this clock, okay? And the way I always remember that is that if you just take the absolute value of this guy here, what do you have to add to this guy to get 12? 2. And that's kind of the way I remember it. And that's going to be true for everything. And of course, this keeps going this way, negative 22, and so on and so on. All you're doing is going around the clock. Modular arithmetic is so easy, and it's so awesome. Some of the things we do, we're going to learn a couple of different, I think we're going to learn 6 or 7 different codes that all have some modular arithmetic in them, and they're kind of fun to do. If a person did mod 6, the only answers you can get on a mod 6 clock are the remainders that you can possibly get when you divide by 6. So when I divide by 6, I can get a remainder of 0, which means it went in evenly. I get a remainder of 1, 2, 3, 4, or 5. If I get a remainder of 6, you just didn't divide big enough, okay? So for instance, 54, 6 goes into 54 8 times with a remainder of 6. No, it doesn't, you ding dong. It goes in 9 times with a remainder of 0. And so what we would say is that 54 is equivalent to 0 mod 6, okay? Notice that it went in evenly, so 54 is also 0 in mod 9, if you're doing a mod 9, because 9 and 6 both go into 54, for instance, okay? If you're going to do some modular arithmetic, if you did 33 plus 47 plus 16, what is this equivalent to in mod 9? I don't know either. If it's me, I'm going to add first. That's 80. That's 16 is 96. I think it's pretty clear. It goes in 10 times with a remainder of 6. There's our answer. Okay. So you look at that, you're like, is there another way to do this problem? Sure. Person could do, how many times does 9 go into 33? Well, it goes in 3 times with a remainder of 6. So in other words, 33 is equal to 6 mod 9. And 47 is equal to 9 goes into 47 5 times, I guess, with a remainder of 2. Is that right? I think so. And 16, 9 goes into 16 1 time with a remainder of 7. If you were to add 6 plus 2 plus 7, you get 15. Good grief. What is 15 in mod 9? Well, 15 divided by 9 is 1 with a remainder of 6. Me personally, I'd rather just get the big number here and do it one time, but you're welcome to do the mods one at a time and pull this off, okay? Modular arithmetic's quite a bit, I don't know, I kind of enjoy it. It's kind of fun. 30 minus 2 times, I don't know, 67, I don't know, whatever, is equivalent to mod 8. Why not? Okay, I can't do that today in my head, so let's do it this way. 30 minus 2 times 67, negative 104. All right, cool. Let's look at it here for a minute. So what is 104 divided by 8? I don't know, 1, 8, 2, 4. Oh, crap, it goes in evenly. No, well, there you go, 0. Okay. That's not what I wanted to do. I'm going to change it here in a second. That's not exactly what I wanted, but it'll work. Okay. Let's make this some other number. Let's make it 33. So 33 negative 101. Let's try that one. So you notice what I did was, I said, listen, I'm not going to worry about the negative right now. Let's just see let's see what's what here. In other words, what we're going to be doing is going around the clock this way. Okay. So 8 goes into 10 one time. 8 goes into 21 2 times, with the remainder of 5. So in other words, it's 8 times negative 12. That means I went around the clock 12 times in the negative direction, and then I went 5 more. Okay. So if you look at this, it's 96 minus negative 96 minus 5 is the negative 101. Again, I personally just dropped the negative there. I think it's easier. Okay. Now, when I look at this, I think to myself, okay, negative 5. Okay, well, let's count it out. Now, I really have a hard time with this unless I draw the picture. I don't know why. It's just tricky for me. So if I start here and I go negative 5, that's 1, 2, 3, 4, 5. Oh, well, yeah, that makes sense because 5 plus what is equal to my mod number, 3. That's going to be the answer. Okay, because whether I went negative 5 this direction or I went positive 3 this direction, I end up in the same location. Okay. I think that's the trickiest one, is when you end up with negative mod numbers. I think they're by far the trickiest. By the way, someone will ask, can Excel do mod numbers? Yes. And yes, we will use them when we get to use that functionality when we get to coding. I'd rather you did it by, I want you to do it by hand now. So I want you to show me that. You can do it by hand. And I want you to show the work on that for the tests and stuff. I think it's a big deal. I think it's kind of a hugely important concept why it works that way. If you cannot explain to me like what you're doing there, then it's going to really screw you up later on when we get to solving these things. You're like, well, wait, why is it that? Why is it this? Okay. In fact, the UPC code, okay, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers in the code. The first, oh, let's wait, hold on. The first one tells you about the product. You don't need to know that. The next 5 are the product number. The next 5 are the manufacturer number. And the last digit's the check digit. And there's a little recipe, is how they use it. But this little guy here is what you'd have to add in order that it's 0 mod 10. Okay. So you're going to be adding something to it so that the answer to this problem they're going to make you do comes out to be 0 mod 10. So if the computer, when you're typing in the numbers, okay, this bottle of ketchup here, and you're typing in 1, blah, 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 and then it goes error. The reason it says error is one of 2 things. Either you typed in a number that you don't sell, so the computer says, hey, there's a problem here, or more likely, maybe you transposed a couple of numbers, you typed a 7 instead of an 8 or what have you, and then the computer, the little math problem that the computer knows to do with the UPC code does not come out to 0 mod 10. And because it doesn't come out to 0 mod 10, that means there's a mistake, okay? And so it's gonna be pretty cool stuff, this modular arithmetic. Again, it's not a very hard concept, but it's gonna be a big deal going forward. And where you're gonna use it this week in class is you're gonna be talking about equivalence relations. And again, it's that idea that 2 and 14 are the same. They're equivalent in mod 12 arithmetic, okay? Or 3 and 10 are equivalent in mod 7 arithmetic, for instance, okay? They are the same thing, right? What time will it be 24 hours from now? The same time it is right now. How do you know that? Because I went on the clock twice. I'm going to get right back to where I started from. It's equivalent. That is one of the easier equivalence things to understand. And so then we look at that from an equivalence class, we're like, that's great. So then when we get over to chapter 2, we start talking logic, you're like, well, instead of saying equivalence class relations, we just say, hey, these are logically equivalent. It's the exact same process. It's just looked at it from a little slightly different viewpoint, okay? Also, I just want you guys, again, to kind of hammer this point home a little bit more, is the idea that in this class, you'll notice the math isn't terribly difficult. It's more the understanding, okay? It's probably one of the first classes maybe that you've taken in math class where it's not just number crunching. it's a lot more understanding concepts. The number crunchings as they are not that hard to do. It's the understanding the process of what it is I'm trying to show that is maybe a little more difficult for you to do for a change. Or maybe you find it easier and more fun, I don't know. I don't know, man, there's something to be said for just crunching numbers, getting an answer and being done with it. But there's something also to understand for like kind of understand a big picture going forward. So that's kind of why I like the class. Anyway, I think that's about all I needed to say about that. Any questions at all about where we're at? Let me know. And again, as far as next week goes, if you came in late, no class next Wednesday, and I'll let you know about office hours at some point during the week. So again, I don't know if I'll be able to broadcast from where I'm going to be. I certainly can answer email though. Taylor, you got the floor. Are you here? Are you going to say something? All of a sudden, my whole screen went Taylor. No? All righty.
I do have a question.
Hit me.
For the homework for last week,
Mm-hmm.
I don't know how much work you wanted, because I wrote down like how I derived the answers.
Yeah, that's all. I haven't looked at your specific homework yet, but yeah, if you just show me how you get there, right? So on some things it's pretty straightforward, like hey, there's 6 sides of a die, it's probably getting a 5 is 1 out of 6. There's not much to say about that. But if you have to do like this, choose this, times this, choose this, divided by this, choose this, or just show me what you did to get there.
You already looked at mine.
Oh, I did. Okay.
Yeah.
I can't remember, to be honest with you. So it's probably enough. I don't think I didn't make any comments, did I?
You said I didn't show as much work, but it was just graphs, and then
Oh,
all I saw was like the past and stuff, and I wrote down the answers.
oh,
So I don't know like how much work you can do with the graphs.
I don't know. Maybe I wasn't. Was I talking about the graphs? Maybe I was talking about something else. I don't know. Don't worry about it. I don't think I marked you down at all. Make sure that you show enough work, I guess, that I can kind of follow you. Yeah, you're right on a graph. You can't really do much on a graph. It is what it is.
But you're marking me down a lot though.
But I think you're missing some problems, not just the work though. I'll go back and look at it. But I think there was something. I remember looking at somebody's last week who was missing quite a few problems, or at least I thought it was, not just the amount of work. I can look real quick here. Of course.
I don't think I was missing any problems.
Maybe I'm just stupid. I don't know. I don't know. I'm looking. Here we go. Homework week 1 and 2. Let's see. I don't know, man. I don't know. Yeah, it looks like you're missing some stuff. It looks like you're missing about half the assignment to me is what I thought. So it looks like to me anyways. I'm pulling it up right here. That's what I made it. It wasn't comment about your actual amount of work you showed. I just thought it looked like you're missing a bunch of problems, like half of it. So like maybe just chapter 1 or just chapter 2. I don't know. I'm looking it up again here real quick.
I did chapter 1 on like the first page, and then chapter 2 on the next 2 pages.
Okay, then I'll go back and fix that. Okie doke. Yep.
Okay, thank you.
No, I guess I didn't see the first week's homework. It was just on the first page. All right.
Yeah, there should have been like 3 pages.
1. Yes, you only see 2 pages. Oh, there's 3 pages. Okay, there's the 3rd page loaded. Okay, that's what it must have been. The 3rd page didn't load. Oh, okay. Yep, there it is. All right, I'll fix that. Check.
Okay, thank you.
Yep, sounds good. Any other questions at all? Anyone? I'll get rid of
Yeah,
that.
I got a question.
Hit me.
Related to, I asked you about this earlier. I just wanted to verify that in the discrete, not this class, the statistics class,
Mhm.
Do I just contact you if I want to do a different time than 6 p.m. for a midterm and final?
Yeah. Yeah, exactly. Yeah, and especially if you could do Wednesday. If you could do Wednesday, like for the midterm, because I think the midterm, I'll have to look. I think the midterm is the same week as the other 2. I think they're all the same week as I have to go look again. But if you could do the midterm, for instance, in the morning, I think it's the same week as my differential equations time class. Then I could just be online, because I don't want to be like tied to the computer all day. It'd be nice to be able to, well, any more than I already am, but it'd be nice to be able to go, all right, I'm already online here. I'm watching these guys and answering questions. I could do the same thing for yours at the same time. But yeah, we'll definitely talk about it. And for the final, for sure, if you could do the morning. So my morning class on Wednesday would be from 10 to noon. So you could have a little longer if you wanted to. You can start a little early or whatever. But yeah, we'll talk about it when the time gets closer.
Okay, that's great. That'll work perfect. And then you were talking about the homework for this class. I remember there was a lot of homework due for both of these classes that was due on the 12th. Did we already have some homework due for this class?
No, I think it's still due the 12th. I'd have to go look at the answer again. I get confused in every class. But no, if it gets turned in, I just on the ball yesterday and graded a bunch of stuff. So.
Oh, yeah, that's what I figured. I got everything done. I just haven't turned it in. All right, thank you.
Yep. All righty. Anybody else? If not, I guess that's it. And I will see you, well, not next week, but I'll be in touch next week. You have something to say, Bobby?
I was just gonna say, have a good week next week. Are you going hunting?
I try to do a little bit of fishing. Kind of my Wallowa. There's the Wanahas up there. I grew up in Washington on the north side, above all that, the Blue Mountains there. But and I've been to Wallowa a ton, but I've never fished the Wanaha. So I'm gonna hike up in there and fish some of that for a while.
Oh, it sounds amazing. Hope you have a good time.
Thanks. I hope so too. All right. Take care, everybody.